Have you ever wondered if a person's background really affects how well they do their job? Imagine a school district where academic administrators come from different socioeconomic backgrounds, some from affluent families, others from middle income, and some from less privileged circumstances. The big question is, does socioeconomic status actually make a significant difference in how these administrators perform, or is it just a myth? What is one-way analysis of variance? By definition, the one-way analysis of variance, or ANOVA, is used to determine whether there are any statistically significant differences between the means of 3 or more independent groups. That's right, 3 or more. It's a test of significant difference. Unlike the t-test or z-test, which compare only 2 groups, ANOVA is used when you have more than 2 groups. So, once you have more than 2 sets of data, you can no longer use the t-test or z-test. You use one-way ANOVA instead. The formula for one-way ANOVA is actually very simple. It's the f-value, also called the f-ratio, which is calculated as the mean squares between the groups divided by the mean squares within the groups. The mean squares between the groups is abbreviated as MSBG, and the mean squares within the groups is abbreviated as MSWG. So, the formula is just a ratio between these two values. But even though the formula looks simple, before you can get the MSBG and MSWG, or the F-test, you have to go through 7 steps. Each step is important to ensure your result is accurate. The decision rule for ANOVA is similar to the t-test and z-test. If the computed f-value is less than the f-critical value at the given degrees of freedom and significance level, you accept the null hypothesis. If the computed f-value is greater than the f-critical value, you reject the null hypothesis. In other words, if your f-value falls within the acceptance region of the normal curve, you accept the null hypothesis. If it falls in the rejection region, you reject it. For this lesson, we'll use the f-table at a 0.05 level of significance, which is most commonly used in research. The f-table uses 2 degrees of freedom, 1 for within the group and 1 for between the groups. The values in the table will differ depending on your chosen significance level, but for this example, we'll stick with 0.05. Let's proceed to our example. Is there any significant difference in the performance of academic administrators when they are grouped according to socioeconomic status? We'll use alpha equals 0.05. Suppose we have 3 groups, low, average, and high socioeconomic status, with the following performance data. Since we have more than 2 groups, we use one-way ANOVA. First, we organize the data and prepare the table for computation. For each group, we square all the data points. 1 squared is 1. 2 squared is 4. 4, 4, and 9. For second group, the squares are 4, 9, 16, 25, and 36. For the third and last group, the squares are 16, 16, 16, 25, and 49. Next is we need to sum them up and also calculate the total for each group and the grand total for all groups. For example, the sum for the first group is 10, the second is 20, and the third is 24. The grand total is 54, and the sum of the square data is 234. It's important to note that the number of data points in each group doesn't have to be the same. In this example, each group has 5 members, but ANOVA works even if the group sizes are different. The same rules that we're doing in our other videos. We will not use the whole table. We only have specific data in that table that we will use, which is all of the ones that are bold. Here are the data that we will use for this example. The sum of each group, the grand total, the sum of all the squares, the sample size for each group, the total sample size, and the number of groups. Now, let's go through the 7 steps of computation. Step 1. Determine the correction factor using the formula. Correction factor equals the grand total squared divided by the total number of observations. So 54 squared divided by 15. 54 times 54 is 2,916. Divide 2,916 by 15, and you get 194.4. Step 2. Determine the total sum of squares, or SS total. SS total equals the sum of all square data minus the correction factor. So, 234 minus 194.4 equals 39.6. Step 3. Compute the sum of squares between groups, or SSBG. SSBG equals the sum of each group's total square divided by the number in that group. Then subtract the correction factor. So for the first group, 10 squared divided by 5 is 100 divided by 5, which is 20. For the second group, 20 squared divided by 5 is 400 divided by 5, which is 80. For the third group, 24 squared divided by 5 is 576 divided by 5, which is 115.2. Add these up. 20 plus 80 plus 115.2 equals 215.2. Now, subtract the correction factor. 215.2 minus 194.4 equals 20.8. Step 4. Compute the sum of squares within groups, or SSWG. SSWG equals SS total minus SSBG. So 39.6 minus 20.8 equals 18.8. Step 5. Compute the degrees of freedom. For between groups, subtract 1 from the number of groups. We have 3 groups, so 3 minus 1 equals 2. For within groups, subtract the number of groups from the total number of observations. 15 minus 3 equals 12. Step 6. Compute the mean squares. Mean squares between groups, or MSBG, is SSBG divided by the degrees of freedom between groups. So 20.8 divided by 2 equals 10.4. Mean squares within groups, or MSWG, is SSWG divided by the degrees of freedom within groups. So 18.8 divided by 12 equals 1.57. Finally, the last step. The step 7. Compute the F value. F equals MSBG divided by MSWG. So 10.4 divided by 1.57 equals 6.62. Now, we compare our computed F value to the F critical value from the table at alpha equals 0.05, with degrees of freedom 2 and 12. The F critical value is 3.89. Once we have the F value, we compare it to the F critical value from statistical tables, based on our chosen significance level, usually 0.05, and the degrees of freedom. Here's the decision rule. If the computed F value is less than the F critical value, we accept the null hypothesis, meaning there's no significant difference between the groups. If the computed F value is greater than the F critical value, we reject the null hypothesis, meaning at least one group is significantly different. Let's look at our example. Since our computed F value, which is 6.62, is greater than the F critical value, which is 3.89, we reject the null hypothesis. This means there is a significant difference in the performance of academic administrators when grouped according to socioeconomic status. So, in our scenario, ANOVA helps school leaders and researchers determine if socioeconomic status truly influences how well academic administrators perform, or if any differences are just due to random chance. Next time you're faced with multiple groups and want to know if they're genuinely different, remember, One-Way ANOVA is your go-to tool for finding real answers in a sea of data. If you found this explanation helpful and want to learn more about statistics, math, and technology, don't forget to subscribe to my YouTube channel, Math and Philtech TV. Hit the like button, share this video with your friends, and leave a comment below if you have any questions or topics you'd like me to cover next. Thanks for watching, and see you in the next video.